Last time we discussed the canonical ensemble and the partition function, and we see how useful it is to determine macroscopic thermodynamic quantities such as energy, pressure, entropy, etc. As long as we can determine the partition function, we can take a number of derivatives of log z to determine these macroscopic thermodynamic quantities. That works if you have a system in contact with a heat reservoir at some temperature T, and of course they're in thermal equilibrium. Even if the system is isolated and there isn't a heat reservoir, but it has a fixed energy, the mean values of the system's macroscopic parameters are related to its temperature T, as though they were connected to a heat reservoir. Again, all we have to do is find the partition function z, which we write, if you might remember, as sum over r, e to the minus beta, e sub r. That's our partition function, where we sum over all accessible states of the system. And as I think you'll see even more today, it's so much easier than using the microcanonical ensemble and trying to count the number of states. So as long as we know what comprises a system and how the constituents interact, we can calculate the quantum states for any system and evaluate the sum. All that remains is the mathematics. For ideal gases, this is going to be easy. For liquids, which we're not going to do, it would be very hard. So again, this is classical statistical mechanics, and for this to be valid, we're going to look at a system that has an energy that depends upon however many coordinates, maybe Q1 through Qf, and momenta, P1 through Pf, such that we have F generalized coordinates and F generalized momenta. What we do is we divide phase space into volume h naught to the f, and we can evaluate the partition function z first by summing over the number of cells of phase space. Well, how do we do that? The number of cells of phase space, we can write as dq1 through dpf, all divided by h naught to the f power. Now, we expect that these states are going to have nearly the same energy E, which is a function of those coordinates and momenta. And then all we have to do is either integrate or sum. So generally speaking, it's easier to integrate than do a sum. So in my classical approximation, I can write my partition function as a whole series of integrals, e to the minus beta e, as a function of q1 through pf times that volume of phase space dq1 through dpf divided by h naught to the f power. Some things to know. The energy of the system can only be determined within an arbitrary additive constant. So if we change all the levels by some constant energy, little epsilon, the energy of each state, my new energy, we'll call it E sub r star, would be equal to the initial energy plus epsilon. And each level would be raised by this amount, shifted by that energy. As such, the entropy, my new entropy in such a configuration, can be written as K times parentheses log of Z star plus beta times E sub r star, or I should say mean beta. And I can write that as K times the log of Z plus beta times the mean energy. So what this is saying is that even though the energy is changing by some additive constant, it does nothing to affect the entropy. So all expressions that involve generalized forces are also going to be unchanged, as are equations of state, simply because they involve derivatives of log c, which will not be affected by the addition of an arbitrary constant added to the energy. That's one thing. Second thing to take note of, suppose I have a system A consisting of two subsystems. We'll call it A prime and A double prime. And let's say they can interact but only weakly with one another. And let's say the states of A prime are labeled by R, the states of A double prime are labeled by S. So the total energy of this combined system I can write as E sub R prime plus E double prime sub S. Now, A prime and A double prime can be two distinguishable groups of particles that interact weakly with one another, or they could even be the same system but two different degrees of freedom. So for example, I might look at one degree of freedom as being translational motion of the center of mass. Another degree of freedom might be the rotational motion, or it could be the vibrational motion. So there are a number of ways to where this can apply. I can write my partition function, z, as sum over r and s, e to the minus beta, e sub r prime plus e sub s double prime. And of course I can write that as a product as well. I can write that as sum over r e to the minus beta e sub r prime times the sum over s e to the minus beta e sub s double prime. What that says is that essentially my partition function is the product of the partition functions of each of the systems. Moreover, if I take the log, which is typically what I'm interested in, the log of the partition function would be the log of z prime plus the log of z double prime. So it's additive. Very nice. So if we have a system consisting of distinct non-interacting parts, I can write the partition function as a simple product, and I can write the log of the partition function as just a simple sum. Knowing that, let's go ahead and do some nice applications. The one that, of course, is ubiquitous in statistical mechanics is the ideal gas. Let's do that one first. So we've got an ideal, and we'll do a monatomic gas. Let's assume we have n identical monatomic molecules of gas, each of mass m, and they're located in some volume v. Okay? We'll denote the position of the ith molecule, maybe that's this one, as r sub I, and give it momentum p sub I. And that's how we would characterize all of the molecules in this ideal gas. The energy, I could write as sum I equals 1 to n, p sub I squared over 2m, plus u of r1, r2, all the way out to r sub n. Now, if the gas is sufficiently dilute, happily for us, this term will be zero. So for a real ideal gas, that sounds crazy. For an ideal gas, typically the potential term will be zero. That will make our life a little bit easier. Classical procedure would be as follows. If I want to find the partition function z prime, I can write that as e, or to the exponent, to the minus beta times this whole mess. So it would be 1 over 2m times p sub 1 squared plus all the way out to p sub n squared plus u of r1, all the way out to r sub n. And then I would, of course, be integrating over d3r1 through d3p sub n all over h naught to the 3 dimensions. And close that off. I can break this integral up into products of e to the minus beta times the energy. So I can break this whole one giant integral into little integrals, and I might write it this way. Z prime is equal to 1 over h naught to the 3n integral e to the minus beta over 2m times p squared, p1 squared, and then I've got e to the minus beta over 2m pn squared, and then I have all my u terms. Integral e to the minus beta times u of r1 to r sub n. And again, d3r, d3p, d3r1 all the way out to d3p. So it's a messy, messy looking thing. But since the kinetic energy is the sum of all the above terms, you got one kinetic energy per molecule, the partition breaks up into a product of n of these integrals. So the kinetic energy term looks generically like this: minus infinity to infinity, e to the minus beta p squared over 2m d3p. In general, when I'm talking about the potential energy, u is a complicated function. It'd be pretty hard to carry out. However, in the case of an ideal gas, the product integral d3r1 all the way through d3rn very simply works out to be just a volume, v to the n. So that's very, very convenient for us. So I can write then, let's write z prime, my partition function, is going to be, it's going to be actually I'm going to define zeta as a one particle partition function, and this would be zeta to the nth power, because each one of those terms would apply the same zeta. That being the case, and of course I can define zeta as my one particle partition function, write that as v over h naught cubed, integral 1 in minus infinity to infinity, e to the minus beta p squared over 2m, p squared over 2m. So this makes things a little bit easier. Moreover, log z prime in this case, would be just n times the log of zeta. Okay, so what I can do now is let's look at our one particle or one molecule partition function and play with it just a wee bit. So for the one particle, I can do minus infinity to infinity, e to the minus beta p squared over 2m d3p. And of course, I can put that in 3 dimensions: minus infinity to infinity, minus infinity to infinity, minus infinity to infinity. And I can write this, in fact, I can write this as the product of 3 integrals. Let me do it this way, make it easier. E to the minus beta px squared over 2m dpx, minus infinity to infinity, e to the minus beta py squared over 2m dpy. And then, of course, minus infinity to infinity, e to the minus beta pz squared over 2m dpz. So I've got a product of 3 terms. By the way, that integral is easily calibrated. It will give me, each will give me 2 pi m over beta to the 1/2 here, so I'll get essentially 2 pi m beta to the 3/2. Therefore, I can write that is my integral. So my single particle partition function, zeta, I can write as v times 2 pi m over h naught squared times beta. Okay, great. That's for one particle. I can say then the ultimate goal is to get log z prime. Log z prime is n times the log of zeta. So that's going to be log of z prime will be n times log of v minus 3/2 log of beta plus 3/2 log of 2 pi m over h naught squared. Okay. Well, now that I have log z, as I promised from the outset, I can calculate a number of interesting thermodynamic quantities. Let's do that. Suppose I want to know the mean pressure. Well, remember the mean generalized force, in this case the pressure, I can write as d log z prime dv. V is my external parameter, p is my generalized force. Using that expression, I can write this as n divided by v times beta. And of course, what this gives me is my equation of state. The old ideal gas law, P v is equal to n KT. So it's the ideal gas law or equation of state follows directly from this operation with the partition function. I want to know the mean energy. The mean energy, remember, is minus d log z prime d beta. If I do that, I get 3/2 times n times beta, or if you like, 3/2 n kt. Again, what we recognize as the mean energy of an ideal gas with n particles in 3 dimensions. Mean energy is 1/2 kt per degree of freedom, and then n times for the n molecules that I have. So this is all fitting very well, and I can take it another step further. Suppose I want to know the heat capacity. Heat capacity is just the derivative of the energy with respect to T, holding the volume constant. And if I do that, of course, I get 3/2 times nk. Again, a familiar result. Well, I'm on a hot streak, and of course I want to calculate the entropy too, because that's one of those desired quantities. And I have k log of z prime plus beta times the mean energy, and that will give me nk log v minus 3/2 log beta plus 3/2 log of 2 pi m over h naught squared plus 3/2. So there's this beautiful expression for entropy. And I can write that. Let me simplify it a little bit, although this seems like a fool's errand, as you'll see. Log v plus 3/2 log, and the rest of the stuff is just junk. We're just going to call it plus sigma, where sigma just stands for all the rest of the junk that we don't want to write out. And you'll see why in a second. So we feel like we're on a hot streak, we're humming along, we got the equation of state, we got the mean energy, now we got the entropy, and here's the problem, we're wrong. The entropy is wrong. It's badly wrong. Let's do a post-mortem and see what happened. First of all, let's make some excuses. We did this classically. It's not valid at low temperatures. We know what happens at low temperatures, or we will know if we don't know yet. We're going to find out at low temperatures. You've got to use quantum mechanics, and weird things are going to happen. So we know that once we get to low temperatures, this thing isn't going to work. Okay. Well, and we will do a quantum mechanical description. That's coming up next, well, soon. Furthermore, as the temperature approaches 0, I should find that the entropy approaches 0. That's the third law of thermodynamics. This is telling me as the temperature approaches 0, log T, log of 0 is minus infinity. Minus infinity, well, that's no good. Oh, again, we're just going to say, well, that's low temperatures. Oh, but that's not the only problem. We have a bigger problem than that. This expression is implying that entropy doesn't behave like an extensive quantity. In other words, if I double the size of the system, I'm not getting double the size of the entropy. Now wait a minute. That's just wrong. Let's see what happened. How did we mess this up? How did we have this problem? Notice, if I multiply volume by some constant alpha, and I multiply n by some constant alpha, notice what happens. Entropy gets increased, n log of v. It doesn't double. So n log of v becomes alpha n log of alpha v, which is no good. That can't be right if entropy is truly an extensive quantity. So we're in some trouble here. Let's take this a little bit further. Let's take a container and let's divide it into two parts by a partition. Now, if I had a container of gas and I stuck a partition in there, I could just as well pull the partition out and nothing should change. Not a big surprise. It's a reversible process. Shouldn't affect the distribution of systems over their accessible states. So with or without the partition, let's say that's entropy S and that's entropy S. The total entropy should be S double prime plus S prime, either way. Now let's see what really happens. If I divide the partition into two equal parts, each containing n prime molecules in volume V prime, the entropy of each part would be S equals S, it's going to be the same, n prime k log of V prime plus 3/2 log of T plus sigma. But the entropy of the gas without the partition is 2n prime k log of 2v prime minus 2n prime k, plus 3/2 log T plus sigma. Now, if I take the difference between the two, I should get 0, but I don't. What do I get? What I get is the difference between S in the first case and minus 2S prime in the second case is not 0. It's equal to 2n prime k log 2. It should be equal to 0, but it isn't. This is what we have called historically Gibbs paradox. As some philosopher once said, there are no paradoxes, it's just that we're using an incorrect paradigm, and that's exactly what's going on in this case. Let's pursue this a bit further in the next lecture. Thank you.